Hello everyone, this is Lecture 7 of ComSci 123, Hash Tables and Skip Lists. In today's video, we will look at hash tables and two techniques to handle hash tables, namely separate chaining and linear probing. We will also look at ordered maps and how to implement them using skip lists. Okay, so let's start. Previously, we talked about maps in dictionaries. So we said that maps and dictionaries both use entries, which are key value pairs. But the difference is that for maps, we have unique keys, while for dictionaries, multiple entries with the same keys are allowed. Okay? Now, we also looked at different implementations of maps and dictionaries. So, for the DLL map that is unsorted, all methods will run in O of n time, because we will need to traverse the DLL, for example, to search for a particular key, to delete the particular key, or insert a particular key. And first we have to make sure that the key is unique, so we'll have to do search first, right? And then for array map, it's more or less the same problem if it's unsorted, right? So we also have to traverse the array to make sure that the key is unique. Or for deleting and inserting, we need to shift items as well. Okay, so all of the methods run in O of n time. For dictionary that is unsorted, however, the one improvement is that insert will now run in O of 1, because we could just insert the entry at the end without having to worry if there are duplicate keys or not, right? Because it's allowed in dictionary. So we'll notice here that the insert already runs in constant time. However, search and delete still runs in O of n, because we'll have to traverse the DLL or traverse the array. And additionally, for array dictionary, when we delete, we need to shift the items back, right? So to avoid having holes. Now, the best implementation that we saw last time was called the search table, which had sorted entries, right? So sorted array, basically. So if you have a sorted array, you could run your search in O of log n, because you can use binary search, right? However, delete and insertion will still run in O of n because of the shifting of items forward and backward to avoid holes in the array. Okay, so those were our previous implementations of maps and dictionaries. And in this video, we will look at two ways that we could improve upon these implementations, and we will be looking at hash tables to improve the performance of map implementation, and later on we will also look at skip lists, which we'll use to implement ordered maps. Okay, so let's start with hash tables. So this is not the hash table that we are talking about, right? So hash on a table, or hashtag table, hash table. This is not it. Okay, so hash table is used to implement maps, and as we said earlier, maps are key value pairs, and in the map, the keys should be unique. Now, keys are usually either strings or numbers. It could be any type of object, but it's usually strings or numbers, right? Now, what if we have prior knowledge about the map's keys? Okay, so for example, what if we know that there are only n possible keys and that they are numbers in the range 0 to n minus 1? Okay, so for example, there are 10 possible keys, and those keys are from 0 to 9. Okay, so that's why it's 0 to n minus 1. So what can we do if we want if we know this information about the map? So a good implementation for this map would be to use an array of size n. Okay, and we will store each entry with the key k at index k. So there will be like a one-to-one mapping. Okay, so it's fairly straightforward. So for example, if you have 10 possible keys ranging from 0 to 9, and let's say this is your map. So you will have an array of size 10. So you have indices from 0 to 9 here. And if you have an entry with key, for example, 0, you would also put that at index 0. Okay? So if this is our map, we would have the following entries here. So 0Z would be placed here. 5F would be placed at index 5. Okay. 3T would be placed at index 3. 8E would be placed at index 8. So it's fairly straightforward. Okay. So whatever is the key, that would also be the index. But that is if the keys are from 0 to n minus 1. Okay. Now, what if it's something different? Okay, so what if it's also n possible keys, but this time the keys are numbers in the range 1 to n. So it's not 0 to n minus 1 anymore. This time it's 1 to n. So for example, if there are 10 possible keys and then it's from 1 to 10. Okay? So we can still use the array of size n, but we will have to do some adjustments. Okay? We can't do if it's if it's at key k, we'll put it at index k. We can't do that anymore. Okay? What we'll do instead is adjust it a little bit so that we can store the entry with key k at index k minus 1. Okay? Does that make sense? So for example, if there are 10 possible keys from 1 to 10, okay, and we will have to adjust the key by subtracting 1 to get the index. Okay? So if these are your indices, okay, and this is your map, where would we put this? Okay, so for 1, this would be at index 0. For 3, this would be at index 2. For 5, this would be at index 4. 7 at index 6. And 10, index 9. Okay? So let's put all of that into the array. So this would be 1, Ichi. 3, Sun. 5 is Go. 7 is Nana. And 10 is Chu. Okay, so we adjusted the indices because earlier we had from 0 to n minus 1, so there was a 1-to-1 mapping between the key to index, but this time it's from 1 to n. So to make this these are our keys, but our indices are from 0 to n minus 1 only. So we have to adjust by subtracting 1. So key minus 1 so that it would be mapped perfectly to this range. Okay? So we did that adjustment. Okay? Does that make sense? Now next, what if it's not 0 to n minus 1 or 1 to n? What if the numbers are in the range x to y for some numbers x and y, wherein x is the lower limit and y is the upper limit? Okay, so for example, we know that the keys are from 4 to 15. So there are 12 possible keys. So what will we do now? What would be the size of our array? Well, the size of the array would be y minus x and then plus 1. Okay, so for example, if it's 4 to 15, then we'll have the 15 minus 4 and then plus 1. So that's 11 plus 1 is 12 because we have 12 possible values. Okay, so this is the way to compute the size of the array if it's from range x to y. Okay, and then we will store the entry with key k at index k minus x. So remember, x is the lower limit, right? So if for example you have key 4, and 4 is the lower limit, so if we subtract 4 from 4, it would be at index 0, which is the first slot in the array, right? So let's see an example. If it's, as we said, 4 to 15, right? And there are 12 possible keys. So the way that we'll transform the key to get the index is by subtracting the lower limit, which is 4. So that would be key minus 4. Okay, so how will that look like? For this one, these are the indices, right? Now, what are the possible keys that could be placed here? So this here would be 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and then 15. Okay, and we get this by subtracting 4 from the key. So key minus 4, that would be the 0, 1, 2, 3, 4, and so on. Okay, up to 11 here. So that would be your indices. So if you put this map here into the array, so 4 Akagi would be placed in 4 minus 4. This will be 0. So it would be placed here, right? 4 Akagi. And then 7 Miyagi would be placed at index 7 minus 4. That would be index 3. So that would be here. So this is 7 Miyagi. And then 14 Mitsui would be placed at 14 minus 4, which is index 10. So right here, 14 Mitsui. Okay, so yeah, we still did some transformations to the key to make it fit the array that we have, okay, to get the index. Okay, next, what if we know that there are only n possible keys and we know that there are integers, but we don't have any idea about the range? Okay, so this time we don't know what the possible range is. So we can still use an array of size n because we know that there are only n possible keys, and we'll store n3 with key k at index k modulo n. Okay, so we'll use modulo, or the remainder, when we divide it with n. So how will that look like? So for example, let's say that we know that there are 5 keys. Okay, so these are the 5 keys here: 44, 102, 28, and 36. So we'll use an array of size 5. We have that one here. And where will we put them? We'll use this transformation, key modulo 5. Okay, so 44, so we have the 5 keys, right? 44, 102, 28, and 36. So these are the keys. If you have k modulo 5, so this would have 4, 2, 0, 3, and 1. So those are their values for k modulo 5. So 44 would be placed at index 4. 102 would be placed at index 2. 20 would be placed at index 0. 8 would be placed at index 3. And 36 would be placed at index 1. Okay? So we don't know about the range, but we know that there are only 5 possible keys. So what we could do is use the modulo. Okay? So that's another example. But now, what if it's not the keys are not numbers anymore? Now, what if they are letters or strings, right? So what if we know, in this example, that the keys are uppercase letters from A to Z? So it's only one letter and it's uppercase. Okay, so what we can do is we can use an array of size 26, since we know that there are only 26 possible keys, right? From A to Z. and we'll store A at index 0, B at index 1, and so on, and then Z at index 25, right? So we are transforming the letter now into an integer, and to do this, we have some function in Python called ord. Okay, so the ord function returns the integer that represents the Unicode character. So if you've encountered this before, you've probably seen this in the past. So for example, if you call ord on the small letter a, this would be 97 because that is the ASCII value of small a. But if you call ord of capital A, that would return 65 because that is the ASCII value of the capital letter A. Okay, so yeah, you can use the ord function to get the numerical value for a letter. Okay, so if we want to make this fit into an array of size 26, so that the indices are only from 0 to 25, right? So we have to transform it like this. So ord of the key, so it will give these numbers, and then minus 65 if it's uppercase, because uppercase A starts at 65. So if we subtract 65, A will be mapped to 0. Okay, and then if it's lowercase, then we'll have to use minus 97 because that is the value for small letter A. Okay, so you can do transformations like this just to go from a letter to an integer. Okay, now what if it's not a single letter anymore? What if the keys are strings, and let's say that it's capitalized? So capitalized means that the first letter is in uppercase and then the rest are in lowercase. Okay, like this. So what if we know that the keys are capitalized strings? We can still use an array of size 26, and we can just take maybe the first letter or the last letter of the string, depending on your preference. Okay, so because we're only using the first or last letter, then there are only possible of 26 still, right? So yeah, so for example, if your keys are apple, boy, and crab, we can use this transformation. So the ord of key 0, so that means that it's the first character or the first letter, and then minus 65 because we know that it's in uppercase. But if it's the last, if you're using the last letter which is in lowercase, then we'll have to use minus 97 because that is the value for lowercase a, remember. So it's either the first letter key 0 or the last letter key -1, so that's the last index. Okay, so if we do it like this, if let's say that we are using the first letter, okay, so if it's for apple, we will get the first letter, which is A, and the ord of A is 65, and then minus 65, so apple would be mapped to index 0. For boy, we'll get the first letter, which is B, ord of B is 66, then minus 65 to be mapped to index 1. And then for crab, we'll get the capital letter C, the ord of C is 67, minus 65, it would be mapped to index 2. Okay, so yeah, and you can also use the last letter if you want to. But what we've been doing so far is we've been taking the keys, which are either strings or numbers, and then we're transforming them to fit into an array of a certain size. Okay, and what we've been doing is actually called hashing. Okay, so It's not this type of hashing, right? When you sneeze, you say hashing. No, it's not that one. So hashing is when you transform a key of any type to an integer in a fixed interval from 0 to n minus 1. And we do this by using something called the hash function. So the hash function is the transformation that we've been doing. Okay, so in the first example, we just used the key directly, and then in the second example, we transformed it by subtracting 1, k minus 1. In the third example, it was k minus 4, and then in the fourth example, it was k modulo 5, and then in the fifth and sixth examples, we took the ORed of the letters and then subtracted 65 so that it could be placed in this range, right? So yeah, that's the purpose of hashing and hash functions. So you map the key of any type to an integer in a fixed interval from 0 to n minus 1. So for our hash function, it looks like this, h of k, and it will give you a value, let's call it v. So h is the hash function, k here is the key, which could be of any type. It could be a string or an integer. And then the v here, we call this the hash value. So this is what the hash function returns, and this is guaranteed to be an integer. Okay, so because we take any type of key and turn it into an integer, so that's what the hash function does. So the hash function is actually composed of two things. So the two components are the hash code and the compression function. So for the hash code, this will convert the key of any type to an integer, and it could just be any integer. It doesn't have to fall under any range. Just as long as you can convert the key to an integer, then that's the job of the hash code. Okay, now the second part is the compression function. So it will take the integer here from the hash code and compress it into the range 0 to n minus 1. Okay, so we actually do these two functions in succession. So for your hash function, you apply the hash code first here, h1, on the key, and whatever integer is the result of the hash code, you pass that to the compression function h2. Okay, so you do that. You do the two functions in succession. Okay, so let's take a look at some examples of hash codes. So they are the ones that convert your keys, which are of any type, to an integer. So one example of a hash code is the integer cast. So for the integer cast, we'll try to reinterpret the bits of the key as an integer. So the binary representation of your key, that could be like a number or a floating point decimal. Okay, will get its binary digit representation and reinterpret that binary digit representation or bits as an integer. Okay, so if it's a 32-bit integer, then that's automatically an integer already, because if your key is already an integer, then there is little to no work needed to be done to convert it into an integer, because it's already an integer, right? But if it's like, for example, a floating point, and if let's say it's 64-bit, then we can just take the upper 32 bits and convert that into an integer. Okay, so you can do that for integer cast. Next is by using the memory address of the key itself. So let's say the key here is a string apple. In Python, you can use the function id and pass in the variable or the object, and it will return the memory address of that object, right, or string. And as we know, this memory address is an integer, right? It's a number that looks like this. So you have now converted your key to a number, okay, by using its memory address. There are other hash codes like component sum and polynomial accumulation that involves more complex computation that transforms your key, usually a string with a variable length, number of characters, and then you try to do some computation to come up with a final integer. Okay, so earlier it was very simplistic what we did for our hash code. We just took like the first letter and converted it into a number, right, using ORD. Okay, but you can do much more complex stuff with your hash codes. Okay, so that's the first part of the hash function. Now the second part is called the compression function, and this will take the integer from your hash code and compress it into the range 0 to n minus 1. So some examples of compression functions are what we've been seeing so far, called the division function, or technically the remainder function, or the modulo. So k modulo n. Okay, so we take the remainder of this division, and we use that as um, the index, basically, because the remainders for division on n would be any number from 0 to n minus 1. Okay, you can also do some multiply, add, and divide. So we abbreviate this to MAD. So instead of just taking the key, first we could multiply it with number a and then add a constant b before taking the division modulo with n. Okay, so it's similar to this, it just doesn't have the multiplication and the addition here. And then you can also do truncation, like maybe if it's a long number like the memory address, maybe you can just use the last 3 digits, something like that. Okay, so for example, if your array is of size 1000, and if you use the last 3 digits, then your possible values are from 000 to 999, which are it turns out the indices of your array of size 1000, right, from 0 to 999. Okay, so you can truncate your integer so that you can make it fall into a certain range, so that's also possible. Okay, so there are also other compression functions out there, but these are the common ones. Okay, you can even design your own compression function for as long as you make the integer fall into this range. Okay, so whatever computation you do, it's up to you. Okay, so those are the two parts of the hash function. So again, hashing is all about using the hash function to transform the key to an integer. So that's the work of the hash code, and then that integer should be compressed into the range 0 to n minus 1. That is the work of the compression function. Okay, so this will allow us to use an array of size n in our map. Okay, so that is what we've been doing so far. So that is the idea for hash table. So a hash table consists of two things. One is the hash function, we'll call it h, and the other one is an array called the bucket array, or also known as the table, of size n. Okay, so you have the hash function and the array. So together, this will make up your hash table. Okay, so we call it a bucket array because it kind of looks like this. So we have an array here, and for each cell in the array, it points to a bucket, right? And sometimes this bucket could contain nothing, sometimes it could contain one thing, or it could contain multiple things. So just like a bucket in real life, it could you could put multiple things in it. Okay, and the reason for this is because in hash tables, collisions are bound to happen. Okay, so what are collisions? Collisions is when two keys are mapping to the same hash value. Okay, so what do you mean by that? So for example, let's say that our hash function is k modulo 5. Now what if we have two keys 0 and 5? So if we apply this hash function, 0 modulo 5 is 0 and 5 modulo 5 is also 0. So they will actually map to the same hash value, which is 0, right? So keys 0 and 5 will collide. Okay, so there is a collision because they are mapped to the same value. Okay, another example is, what if we use the first letter earlier, right? So let's say we have two keys, apple and ant. So if we take apple, the first letter is A, right? And A will be mapped to 0. And then for ant, we will take A as the first letter and A will also be mapped to 0. So they are both mapped to 0. So the two keys, apple and ant, will also collide because they are mapping to the same index value, 0. Okay, so those are collisions and they are bound to happen in the hash table. So that is why for each cell we put a bucket in it, because there could be possible collisions. Okay, so going back here, so we need to handle collisions because they are inevitable in the hash table. Okay, so collision is defined formally as when different entries are mapped to the same cell in the hash table, and this happens when the hash function computes the same hash value for two different entries. Okay, so they are two different entries but they are pointed to the same cell. Okay, so there is a collision. So we have to handle these collisions for our hash table to work properly. So today we will look at two main collision handling schemes, namely separate chaining and linear probing. Okay, so let's start with the first one, which is separate chaining. So what is separate chaining? So we know that our bucket array, or just simply the table, has n cells because that is the size of our array. Now for each bucket or each cell, a sub I, this will hold a list of entries that have the same hash value I. So all the collisions will be placed in this list, basically. Okay, so it will look something like this. So if 54 is mapped to 2, 28 is mapped to 2, and 41 is mapped to 2, then at index 2, this will hold a list of all items that were mapped to index 2. So we have the 54, 28, and 41. For index 5, there's only one so far, but maybe later on we can add more items here if there are more keys that are mapped to index 5. Okay, but the idea is for each cell, they could point to a list of items that are mapped to that cell. Okay, so that's why it's called separate chaining, because for each cell there is a separate chain or a separate list. Okay, so that's the idea. So in separate chaining, what we're essentially doing is we're dividing the map into mini maps at each cell. Okay, so we're doing like division of labor, and we're delegating, we'll be delegating the map methods to the mini maps at each cell. Okay, so we said earlier that they are a chain or a list. So the map at each table cell will be a list based map. Okay, so you can use SLL or DLL, but SLL could be SLL based map is enough. Okay, you don't really need to use DLL. So we have to make sure, however, that the list based map at each cell should be as small as possible for this to be efficient. Okay, because we know that list based map runs in O of n, So if n is small, then that should run fast, right? But if n is long, or if n is large, then it will not be as efficient. Okay, so we can accomplish this if we have a good hash function wherein the entries are distributed evenly. Okay, so how does that look like? So let's say, for example, we have let's say a hash table with that uses separate chaining. So let's say that um, a lot of entries are mapped here at index 0, and then only few at other indices. So this one is bad. Why is that? Because at index 0, it has a very long list, whereas in others, it's a short list. So it's not evenly distributed. Okay, what would be good would be something like this, maybe. Okay, so maybe here you have 2, here you have 1, here you have 1. Okay, so at least this one, even if it's not exactly even, but it's almost evenly distributed. So this is good enough. Okay, so it's bad if in one cell there's a long list and then others are either short list or worst empty lists. There's nothing in the other cells. Okay, and then you're maybe concentrating a lot of the entries in just one cell. Okay, so this one is a bad distribution. Okay, so our goal is to have something like that looks like this, evenly distributed. Okay, so yeah, so let me delete this first. Okay, so let's take a look at the different map methods for separate chaining. So get the key. So basically we will compute the hash value using the key. So we'll use the hash function h of k, and let's say that the value that was returned was I. So we'll start at this index. Okay, at index I. Okay, we'll use the list based map at that index a sub I, and then we will call get k on that minimap, because we know that this is also a smaller map at a sub I. So we'll just delegate the get call to this minimap. Okay, and then for put, it's more or less the same. We'll get the hash value for the key k, and then we'll go to index I, the list based map at index I, and then delegate this put call again on the minimap, and then we'll update the size if this is a new key. Okay, so if it's a new key, then we'll increase the size, but if it's an existing key and we only did an overwrite of the existing value, then we won't update the size. Okay, and then for remove, again, it's more or less the same. We start with the hash value of the key, and if through that we get the index, and then we'll use the list based map at that index, and then we'll delegate the function call for remove to that minimap at that index. Okay, and if the key was removed, then we'll update the size, so we'll decrease it. But if the key did not exist, so there's nothing to be removed, so we won't update the size. Okay, so those are the three main methods for the map in separate chaining. So let's take a look at an example, a concrete example, to put all of this into to action, right? So first, we have the following method, so we'll do this in order. Our hash function is the key %5 or key modulo 5. Okay, so remainder 5. So 11R, so 11 remainder 5 is 1, right? So we'll put this at index 1. So this is the list. This will have 11R. Okay, so that's our first entry. Now 23J, 23 modulo 5 is 3, right? So we'll put this at index 3. This will be 23 j. Okay. 7m, 7 modulo 5 is 2, right? So we'll put this at index 2. This is 7m. So we'll put it here. And then 16d, so 16 modulo 5 is 1. So we'll also put it at index 1. So we already have 11r here, so we'll add this to the end. 16d, because 16 does not exist yet, right? So it's safe to add this one here. Next is 24k. 24 modulo 5 is 4. So we'll put this at index 4. 24k right here. And then finally 66f would be at index 1, right? 66 modulo 5 is 1. So 66 does not exist here, so we can add it safely to the end here. 66f. Okay. Now, how about if we do get 16? So 16, what index should this fall into? So 16 modulo 5 is 1, right? So we'll have to consult the list at index 1. So from here, is this 16? No. Is this 16? Yes. So we have found 16. So we'll return 16d as the entry. Now how about get 19? For 19, we'll have to start at index 4, right? Because 19 modulo 5 is 4. So at index 4, well, is this 19? No. And then it's the end of the list already. So we know that 19 does not exist. So there is nothing. Okay? For get 19. For get 10, 10 modulo 5 is 0. So there's no remainder, right? So we'll have to go to index 0. But since there is no list at all at index 0, so we know that there is no key 10 in the map. Okay. Next, get 23. If it's 23, then it's at index 3, right? And then at index 3, you can find it right away at the first node, so we'll return 23j. Okay. Finally, let's take a look at the remove examples. Remove 16. So 16 will start at index 1, right? So 16 here. So we'll start here. Is this 16? No. Is this 16? Yes. So what will happen is we'll have to delete this. Okay. We'll delete this. And we'll have to link this to here. Okay. So we'll have to delete this one. So now that it's deleted, the only two left are 11 and 66, and we have to relink this also, right? Next is remove 7. So 7 would have to look at index 2, right? So at index 2, 7 is found, so we'll remove this one. So now this one will be removed. So this one is actually going to be an empty list already, right? And then for remove 20, 20 is at index 0 supposedly, if it exists, but we know that 0 is an empty list, so there's nothing to remove here. Okay, nothing to remove. And then remove 33, this would be at index 3, but at index 3 we try to search for it, so 23, and then we reach the end of the list without finding 33, so 33 does not exist here. Okay, so yeah, so 33 does not exist. Okay, so what if last one will remove 11? Okay, so 11 should start at index 1. So it's found here at the first. So now the list should start with 66F. Okay, so we'll remove this here, and we'll have to make sure that 66F is the first item on the list. Okay, if we remove the key with 11. Okay, so that is the example for separate chaining. I hope everything is clear on what you need to do for put, get, and remove. Okay, so basically you just start with applying the hash function to get the index. Okay, and then once you get the index, then you delegate the addition or the searching or the removal to the list at that index. Okay, so yeah, that is separate chaining. So what are the pros and cons for separate chaining? The advantage is that it's a growable hash table, because although the bucket array itself has a fixed capacity, but since at each cell we can have a list, then basically it's growable, so it doesn't have any bounds, right? So you can just continually add more and more items here since it's a list. Okay, so that's one advantage. It's also simple to implement the insert, remove, and find methods for separate chaining. However, the disadvantage is that there are n extra lists needed, so you have more memory consumption. Okay, because you need to have a list at each cell, or yeah, at each cell. So yeah, so more memory for separate chaining. Okay, so that's separate chaining. Now let's take a look at another way to handle collisions, which is open addressing. So open addressing is a general technique for collision handling, and in this technique we store the entries directly into the bucket array, and we only store at most one entry per bucket. So there's no more concept of a list for each bucket. Okay, each bucket can only hold one entry, at most one entry, so it's either empty or not. Okay, if it's not empty, then it only has one entry. Okay, so now what do we do when there is collision? So in open addressing, the colliding entry will be placed in a different cell. Okay, so if it's already occupied, if the cell that you're supposed to be in is already occupied, then you try to look for the next empty cell that you can insert yourself into. Okay, so that's why it's open address, because supposedly you're supposed to be inserted at this hash value, but if it's already occupied, then you look for another address. Okay, so there are multiple types of open addressing techniques, so like linear probing, quadratic probing, double hashing, cuckoo hashing, but we'll focus on linear probing in this video. Okay, we'll also mention the other three later, but our main focus is on linear probing because it's the simplest one out of the four so far. Okay, so what is linear probing? For linear probing, what we'll do is if there is a colliding entry, we will place it in the next circularly available table cell. Okay, so let's try to break this down. If it's if there is a collision, we will try to probe, and probing just means that we'll try to check the next cell if it's available. So if if this cell is available, then you can insert it there. But if it's not available, then look for the next one. Okay, and take note that it's circularly available. So we've already seen the concept of circular arrays, wherein if we reach the end of the array, we can go back to the start and continue searching from there. Okay, so that's the probe part. Now, what is the linear part? For linear, this just means that we need to check the next cells one by one. Okay, so we need to check it one by one, because later on we'll see that other open addressing techniques could like skip to other cells and they don't check it one by one. Okay, so in linear probing, you have to check it next cell, then the next cell, and then the next cell, and then you need to wrap around if necessary if you still haven't found an empty cell yet. Okay, that's the basic idea for linear probing. So let's see an example of this in action so that you can understand what it means. So we have some keys here, and our hash function will turn this into the range 0 to 12 by dividing it or taking the modulo 13. So k modulo 13. Okay, so for key 12, k modulo 13 would be also 12, right? So since it hasn't reached 13 yet, and since 12 is currently open, so we'll just put 12 here. Okay, since it's available. Now 18 modulo 13, this would be 5. Okay, and 5, the index 5 is open, so we'll put 18 here. Okay, so far no problem. 41 modulo 13, the closest multiple is 39, right? So 41 minus 39 is 2, so it's remainder 2, and index 2 is also open so far, so we'll put 41 here. 22 modulo 13 is 9, right? And since index 9 is also open, we can just put 22 here. So far no problem, right? But how about the next one, 44? So the closest multiple of 13 is 39. So 39, 44 minus 39 is 5. So it's supposed to be at index 5. But take note here that index 5 is already taken, right? So index 5 already has 18 inside. So we cannot overwrite this one here. So what we'll do is we will check for the next available cell. So 5 is taken, so let's check 6, the next one. 6 is empty, so we could put 44 here. Okay, does that make sense? So since the original 5 was not available, we placed it to index 6. Okay. Next, let's try 59. So for 59, this one is actually 26, 52, right? 52 is the closest multiple, so the modulo 13 is 7. Index 7 is still open, so it's safe to put 59 here. You don't overwrite anything. But for the next one, 32, the closest one is 26, so that's 6. Okay. So it's supposed to be at index 6, but index 6 is already occupied by 44 right here. So we'll have to probe. So 6 is taken, 7 is also taken, 8 is empty, so we can put 32 here. Okay, so from supposed to be index 6, we ended up at index 8. Okay, now how about for 31? 31, well, just modulo 13 is 5, but 5 is already taken, right? 5 is taken, so it's not this one. 6 is also taken, not this one. 7, no. 8, no. 9, no. So we actually end up putting 31 at index 10. Okay, because all the other adjacent cells were already taken. Okay, now how about 73? 73 is actually modulo 13 is 8. Okay, but 8 is already taken, so we'll check. 9, it's not. 10 is not available. 11 is free, so we can put it here. So 73 can be placed here. So from 8, we actually ended up putting it at 11. Now how about if we add 21? So 21 modulo 13 is 8 also, right? So we just did this process earlier. So from 8, it's not available. 9 is not available. 10 is not available. 11 is not available. 12 is not available. So what will we do at this point? What we'll do is we'll wrap around and go back to the start, because this is a circular array. Okay, 0 is available, so we'll put 21 here. Okay, so from index 8, we actually ended up at index 0 because it was the next circularly available cell. Okay, so that's the basic idea for linear probing. Okay, try your hash value first. If that's occupied, go to the next cell. If that's occupied, go to the next cell. If you've reached the end of the array, go back to the start. It's a circular array anyway, and only stop until you've found a empty cell to insert into. Okay, so that's the idea for linear probing. Okay, next, let's take a look at the different map methods and how they're being done in linear probing, starting with search, which is get k, right, the key k. So we start with by computing the hash value of the key k. Let's call that hash value I. So we'll start at index I, and then we'll probe consecutive cells until either the entry with the key k is found, or if you've found an empty cell. Okay, so you start at index I. If the key there is already what you're looking for, then you stop. Otherwise, you go to the next cell, and then wrap around if necessary, until you either find it or you find an empty cell. Because if you find an empty cell, that means that you are sure that the key is not in the map currently. Okay, so as I mentioned, you need to wrap around if necessary because it's a circular array, and you also need to stop if you've probed all cells. So there are only n possible cells, right? That's the size of our array. So if you've already done n number of probes, then you need to stop because you've checked all possible cells and you still haven't found it yet. Okay, now we will also need to skip over something called available cells. We haven't mentioned yet what available cells are, but for now, just know that if it's an available cell, we will skip over it and continue the probe. Okay, so I'll explain in the next slide what available cells are. Okay, so but just keep in mind for now that if it's an available cell, we need to skip over it. Okay, so let's take a look at the next method, which is remove, or the delete method. Okay, so we'll use basically the same process as the get or the search, and once we find the entry, okay, we'll remove that entry from the cell and mark the cell as available. So this is what we meant earlier when we said available cells. Now, what is the difference between an available cell and just plainly an empty cell? Okay, so remember that in our search, if we find an empty cell, we stop the search, right? But if it's an available cell, we just skip over it and we continue to the next one. Okay, so if we don't convert the the cell with the previously has an entry and then we deleted it, If we convert it directly into an empty cell, okay, if we leave the cell empty and we don't make it an available cell, then your search procedure will fail. Okay, so I'll show you an example. Let's say that our hash function is k modulo 5. Okay, and let's say that we need to insert the keys 11, 21, and 22. So 11 modulo 5 is just 1, right? So this would be inserted at index 1. So we'll insert index key 11 here. Now 21 modulo 5 is also at index 1. Okay. So we start at index 1, but it's occupied, so we'll end up adding it at index 2. Okay. And then for 22, it should be at index 2, but since index 2 is occupied, we'll add it to the next one, which is index 3. Okay, so we've now inserted our keys. Now, what would happen if we delete the key 21? So if we delete the key 21, how would that look like? So the process would start at 21 modulo 5 is index 1, right? So we start at index 1. Is this 21? No. Go to the next one. Is this 21? Well, actually, yes. So we'll remove this one, right? And if we just plainly erase this, okay? So if we just erase that one, it becomes an empty cell. Now, what would happen? So if this is an empty cell, what would happen now if I search for key 22? If it's key 22, it should have started at index 2, right? Because that's 22 modulo 5 is 2. But at index 2, we already see an empty cell. And we said that if it's an empty cell, we stop, right? So, since we see an empty cell at index 2, then we stop our search. And we say that we did not find 22, when in fact, 22 was here all along, right? So that is the danger of leaving cells empty after deletion. So that's why we need to make it an available cell. So instead of just plainly deleting, earlier there was 21 here, right? And then we deleted it. So instead of just plainly erasing it, okay? So instead of just erasing this, we also need to mark this as an available cell. So the way that we'll mark available cells is by maybe by marking it with an X. Okay, so if it's marked with an X, it means that there was an entry here earlier, but we deleted it. So this one is available. Don't skip this when you search, because the key that you might be looking for could have been after this still, right? Because if it's an available cell, we just skip over it, right? Okay, so if we search key 22 here, we start at index 2, it's an available cell, so we skip over it, and then we go to 22, and then we find it, which is the correct behavior, right? So that is the difference between an empty cell and an available cell. So if you leave it empty, it will break the search. Okay, so it will mess up the search procedure. So just mark it as an available cell after deleting. Okay. And then finally, the insert method, which is put kv. So we need to check if the table is full, because if the table is full, then you can't insert anymore, right? So you need to throw an exception for that. So there must always be at least one empty cell left, right? Empty or available cell. And then, as usual, we start at index I, which is the hash value, and then we'll probe consecutive cells until we find either an empty cell or an available cell. Okay, so we can insert new entries at an empty cell or available cell. Okay, So let's call that the cell X, and again, don't um, forget to wrap around if it's necessary. And then whatever cell we ended up with, okay, whatever empty or available cell we ended up with, that is where we store our entry KV. Okay, so yeah, that's the three main methods for the map for linear probing. So let's try to put all of this together in an example. So this was the um, hash table that we created in the earlier example. And so let's continue with this one and go through each method here. So as usual, our hash function is still key modulo 13. Okay, so if we get 26, 26 modulo 13 is 0, right? So we'll start at index 0. So we'll start here at index 0, and then is this 26? It's not. Check the next index. 1 is already empty, so we know that 26 does not exist. Okay, so there's no 26. Okay, next, what if we try to put 16? So 16 modulo 13 is 3, right? So we check index 3 right here, and index 3 is available. It's actually empty, right? So since it's empty, we can just put the key 16 here. Okay, so it's a safe to insert. Next, put 24. 24 modulo 13 is 11, right? So we'll check index 11, but index 11 is occupied. So we'll check index 12. It's also occupied. So we'll wrap around and go back to index 0. This is also occupied. But index 1, the next one, is empty. So we can put 24 here. Okay. Next, how about removal? For remove 32, so 32 modulo 13, 26, 6, right? Index 6. So we start at index 6. Okay, so let me erase this ones first. Erase the extra markings. Okay, so we start at index 6. Is this 32? No. Is this 32? No. The next one, is this 32? Yes. So we'll actually remove this and make it available. So we'll make this an available cell. Okay. So we actually did remove 32, right? Next is 25. So for 25, 25 modulo 13 is 12, right? 12. So we'll start at index 12. Is this 25? No. And then we'll wrap around, go to index 0. Is this 25? No. Next one, is this 25? No. Is this 25? No. Is this 25? No. And then at index 4, it's already an empty cell. So we'll stop our search. Okay, so we did not actually remove 25 because 25 did not exist in the map. Okay. Next is at remove 31. 31 modulo 13 is 5, right? 5. Okay. So we start at index 5. Is this 31? No. Is this 31? No. Is this 31? No. 8 is an available cell, so we'll just skip over it, okay? Because we won't stop prematurely because 31 could still be after this. It's just that this has already been evacuated by the previous entry. Okay, we deleted the entry that was previously occupying it. So we'll check the next one. Is this 31? No. Is this 31? Yes. So we'll also remove this and make it an available cell. Okay, so yeah, we did remove this one. Okay, so now next, let's get 32, and we already know that 32 is starts at index 6, and we previously removed 32 earlier. Okay, so let's try to erase this one first, and then starting at index 6, is this 32? No. Is this 32? No. Is this 32? No. This was actually the spot where we deleted 32 earlier, but we don't know that right now. So we just know that this is an available cell, so we just skip over it. Okay, is this 32? No. Is this 32? Well, it's an available cell, so we'll also skip over it. 32? No. 32? No. This is not 32. This is not 32. Until we reach 4, index 4, wherein it's empty. So 32 actually does not exist in the map anymore because we actually deleted it earlier, right? So we stop already because we found an empty cell. Okay, so yeah, and then next, get 22. So for 22 modulo 13, that would be 9, right? And then at index 9 we actually find 22, so we can just give this directly back. Okay, so we've found 22. How about 24? For 24, this would be at index 11, but at index 11, it's not 24. Index 12, it's not 24. Index 0 is not 24. At index 1, we found 24. So yeah, we found get 24. Okay, for get 19, 19 modulo 13 is 6, right? So okay, so we start at index 6. Is this 19? No. Is this 19? No. This is not 19. And then we just skip over the available cells. Okay, this is not 19. This is not 19. It's not 19. This is not 19. And then we reach 4, which is empty, and then we stop our search because 19 does not exist since we've already found an empty cell. Okay, so that's the difference, right? If you see an empty cell, you stop the search. If you see an available cell, you just skip over it. Okay, and then just the last two methods for put 20. So index would be at 7, right? So 20 modulo 13 is 7. So starting at 7, 7 is already occupied. So we'll go to the next one, 8. So 8 is actually available, so we can put 20 here. So what we'll do is I'll just make this 20. Okay, so I can put 20 here now because this was an available cell, so you can just insert 20 here. And then finally put 41. 41 modulo 13, closest one is 39, so 2, right? So at index 2, put 41, but 41 is already in here, so we won't actually add a new entry, we'll just overwrite this one. So this one will do an overwrite. Okay, so it will overwrite the existing entry because the key 41 already exists. Okay, so yeah, those are some examples of linear probing in action. Okay, so hopefully you understand how linear probing works now. So what are the pros and cons of linear probing? So unlike in separate chaining, we don't need extra memory, right? So since we're just using the basic bucket array, however, the disadvantages are that the insertion and removal tend to become more complex because of the probing and going to the next cell and then going around, doing a wrap around and then checking if it's available or empty. Okay, so the process of the three main methods becomes more complex. And we also have a fixed array capacity, so you need to make sure that your bucket array is big enough to hold all of the entries in the map, right? Otherwise, it will become full and then you won't be able to add anymore. And then lastly, linear probing is also prone to the so-called primary clustering phenomenon. Now, what is this primary clustering? So basically, primary clustering happens when the colliding items tend to lump together, just like what happened in our previous example, right? So earlier here, the colliding items here tend to lump together right here. So going back here in primary clustering, this is a problem because this causes future collisions to have longer sequence of probes. So the more that you lump together collisions, then the worse it becomes for future collisions, right? Because the insert will take longer because you'll have to step through a long cluster to find the vacant bucket. And search will also take longer because the entry will get placed further away from their original hash value index. Okay, so instead of like at index 5, maybe you actually end up wrapping around and inserting it at index 0, right? So it becomes a longer process if there are long clusters of collisions bundled together. Okay, so this is a primary clustering problem. So how about the performance of linear probing in general? So in the worst case, linear probing could take up to O of n time for the three methods, search, insert, and remove. And this happens when all keys inserted into the map actually collide. So when all of the keys um, have a collision. So at the worst case, it will take O of n because you will have to pass over a lot of items first before going to your intended key, right? So yeah, that's the worst case. But in reality, the performance of the linear probing hash table is the it's dependent on the load factor. Okay, so the so-called load factor, which we denote by alpha, is computed as n over c, and n is the current number of entries in the map, and c is the capacity of the bucket array. So the load factor is basically just a measure of how full the hash table is. Okay, so this will affect the performance of your linear probe. So as I mentioned, the load factor is a measure of how full the hash table is, and as the table fills up, then the load factor will increase, and in turn this will increase the chances of collision, and it will also increase the time for you to insert, to find items, and remove items. Okay, so the higher the load factor, the higher the running time. Okay, so the more full, or yeah, the fuller the hash table becomes, the longer it takes to do the methods. Okay, so for each insertion, the expected number of probes is denoted by 1 over 1 minus alpha, which is the load factor. Okay, so for example, if alpha currently is like 0, meaning there are no entries yet. Okay, so it's still empty. So the expected number of probes for insertion would be 1 minus 0, which is 1. So that is good because you only need to probe one time. However, um, as the load factor increases, like let's say 0.5 already, so it's already half full. Okay, so this becomes 1 over 1 minus 0.5, so this becomes 1 over 0.5, so it becomes 2, right? So it becomes more number of probes, expected number of probes, so it becomes fuller. And then let's say at 0.9, maybe it's almost full, almost full. So 1 over 1 minus 0.9, so this becomes 1 over 0.1, so it becomes about 10, right? So now you need about 10 probes for insertion, so something like that. So you see that as the load factor increases, the number of probes for insertion also increases. Okay, so yeah, so that's why the load factor is important. And the hashing efficiency and the load factor are actually inversely proportional. So the higher the load factor, the lower the efficiency. So if you have a low load factor, then you have a high efficiency. So they're inversely proportional. So we mentioned already that the worst case is O of n, and that is when all of the keys are have a collision, but that only happens if you have a really bad hash function, right? If everything collides. So in reality, the expected running time is like O of 1, constant time. So in practice, hashing is fast as long as the load factor is not close to 100%. Okay, so in practice or in reality, it doesn't really take O of n most of the time. It's around O of 1, constant time. Okay, so linear probing it's good. Okay, so yeah. Okay, so that is linear probing. Now, other open addressing techniques include quadratic probing. So what we do here is we kind of increase the spacing between slots during the probe. So for example, you try the hash value first. You try at the index of the hash value, but if that fails, then you, instead of going to the next one, okay, you try at hk, this is the hash value, plus 1 squared and then modulo n, because it might exceed the range of the array. And then if that is still not available, then you go to hk plus 2 squared modulo n, and then if that's still not available, 3 squared modulo n, and so on. Okay, so you'll notice that for linear probing, it was try first at h of k, and then after that, if not available, h of k plus 1, and then modulo n, because it might be we need to check if it has already exceeded, and then if not, then we go to plus 2, the next one, and then if not, go to the next one, plus 3. So this is linear because you're the step for the slot is by 1. Okay, plus 1 plus 1 plus 1. Here it's plus 1 squared plus 2 squared plus 3 squared. That's why it's quadratic. Okay, so let's see just one example of quadratic probing. So let's say that our hash function is k modulo 7. Okay, and remember that if we our next probe is plus I squared and then modulo 7, and then these are the keys that we'll add. Okay, So 50 modulo 7. Okay, so let me write k modulo 7. So 50 modulo 7 is 1 because of 49, right? 49 is the closest multiple of 7. So 1 is still available, so we'll put 50 here. Next, 700. 700 is a perfect multiple of 7, so this is 0, k modulo 7, right? So 0 is also empty, so we'll put 700 here. Now for 76, this is modulo 6. Modulo 7 is equal to 6. And 6 is still open, so we'll put 76 here. But for 85, 85 is, the closest one is 84, right? So this will be 1. But 1 is already occupied. So when we retry, we'll try at 1 plus 1 squared, then modulo 7. So this would be equal to 1 plus 1, so 2. So 2 is still empty, so we'll put 85 here, right? So 85. Okay. Now for 92, 92 is modulo 1 because the closest one is 91 right now, right? But as we said, 1 is already taken up, so we'll retry. So that's again 1 plus 1 squared modulo 7. This is a 2, but 2 is also occupied, so we'll try the next one. 1 plus 2 modulo 7. 2 squared modulo 7. So this is 1 plus 4. So that's 5 modulo 7 is 5. And 5 is empty, so we can put 92 here. And then for 73, this is modulo 3. 3 is open, so you can put 73 here safely. And then finally 101 is also modulo 7 is 3. But then 3 is already occupied, so you have 3 plus 1 squared modulo 7. This is 3 plus 1 is 4, and 4 is empty, so you have that one here. Okay, so that's quadratic probing. So you don't just check, basically you don't just check for the next cell if it's not available. You check for starting at HK. If it's not available still, you go to plus 1 squared, and then if it's not available, plus 2 squared. If it's not available, plus 3 squared, and so on until you find an available slot. Okay, so yeah, that's quadratic probing. Next is another technique for open addressing is called double hashing. This is not when you sneeze 2 times, no, it's not that one. Double hashing is when you use another hash function to find the next slot if a collision occurs. So you have 2 functions. You use h1. If the hash value is occupied, you use h2. Okay, and yeah, so that's basically that's it. So you follow this kind of equation. So at the first try, at iteration 0, so h2 will not be a factor, and then on the first try, if it fails, then it's 1 times the second hash function, and then the next time it's 2 times the second hash function, and the next time it's 3 times the value of the second hash function. Okay, so until you find your empty slot. H2 should not return 0 because otherwise this would just be a single hash function, right? Because if it's 0, then you're not adding anything. And it must also be designed in such a way that it will probe all cells eventually. okay, so that you actually examine everything. Okay, because in linear probing, we are assured that we will examine everything because we're going through it one by one. But here, if you have some fancy computations, maybe you're just probing some cells, and then you're missing out on some cells because of your computation. So you must be careful during your design that it actually examines everything. Okay, so that's double hashing. And then finally, the last one is the cuckoo hashing, which also uses two hash functions. So first you use h1. If the hash value there is not available, then you use h2. If it's still not available, then this is what you'll do. So if both h1k and h2k are occupied, then you will overwrite h2k with the new key that you want to add. So the old key at h2k is displaced, and then you repeat this process with the displaced key. So you basically add it back again. Okay, so for for this key, compute its h1 again. So if it's occupied, or if it's occupied, go to h2. If it's not occupied, then you place this old key there, basically. Okay, so you repeat this process until no displacement occurs. So this is named from the behavior of the cuckoo bird, which actually throws out their eggs once they hatch. Okay, so they displace the eggs. Okay, so yeah, that's open addressing. Okay, so I just want to mention one last thing about designing hash functions. So when designing your hash function, this is dependent on your data set. Okay, so one hash function could be good on this data set, but then it becomes terrible in another one. Okay, so it's dependent on the data that you use it on, and yeah, the design itself. So when you design the hash function, your goal is to disperse the keys as equally as possible among the hash table slots. Now you won't achieve perfect uh, equal distribution, so it's foolish to aim for perfect distribution, but almost equal distribution is good enough. Okay, so your goal is to minimize collisions as much as possible, whether it be separate chaining or linear probing. So try to design your hash function in such a way that it will minimize collision. Okay, and you also have to worry about the time and memory trade-off. What do you mean by this? No, in some cases you will have to go with faster time, or in some cases you would have to go with like better memory or low memory requirements. So let's show an example of that here. That time and memory trade-off. So let's say that your keys are student numbers of this form, like 20, 21, 1, 2, 3, 4, 5, something like that. Okay, so if your keys are student numbers, if you use an array size of 100, then you can use the last two digits of the student number, because the last two digits would be from 00 to 99, right? And that would be the indices of the array of size 100. But if you use array size 1000, then you can use the last three digits, okay, because that would be 000 to 999, okay, and that would be the index for size 1000 array. Or you can also do something like size 500, somewhere in the middle. You can also use the last three digits, but then you'll have to divide it by 2. Okay, so what do you mean by this? Okay, so let's see here. Okay, so if it's 500, so you can use the last three digits, right? So it could be 0, 1, 2, 3, up to like 999, 998. Okay, so if you divide it by 2, So 0 divided by 2 is 0, 1 divided by 2 is 0, 2 divided by 2 is 1, 3 divided by 2 is 1, and so on. And then this one will be 499, 499, right? So there will be some collisions, but at least you have um, compressed it to the range 0 to 499. Okay, so yeah. And then, so what is the time memory trade-off here? If you use fewer digits, like only 2 digits, then you can use a smaller array, but there is uh, more chance of collision because you only have 00 to 99. Okay, so there's more chances of collisions. Now if you use more digits, there's a lesser chance of collision because it's now from 00 to 999, so you have 1000 possibilities, whereas compared to here there's only 100 possibilities, right? But then you will need a bigger array because this one has a size of 1000. Okay, so that's the time memory trade-off. So here you have a smaller array, so that's good memory, but you have more collisions, so that's bad in terms of time. And here you have lesser collisions, so that's good in terms of time, but you have a bigger array, so it's bad in terms of memory. Okay, so you have to be careful around those trade-offs. Okay, so that's it for hash tables. So to summarize, hash tables is composed of two things. You have the hash function and the bucket array. Okay, and then we discussed the two main ways to handle collisions, wherein you have the separate chaining, so you have a different list for each bucket, and then the other one is linear probing, wherein you only have one entry per bucket, and then if it's occupied, you find the next cell. Okay, so that is hash tables. Okay, so next we'll discuss ordered maps, and these are not maps that you like ordered online or ordered from a waiter, but by order we mean that we are sorting the map. Okay, so we know that maps are an unordered collection of key value entries, and whether it's sorted or not actually depends on the implementation. So we've seen map implementations where it's unsorted DLL or unsorted array, and we also saw implementations wherein it's like the search table, right, wherein it's already sorted. Okay, but in some cases we might want to keep the entries of the map sorted, and we want to look up the keys based on this certain ordering. Okay, so that is where ordered maps will come in. So examples of this would be, for example, if your keys are timestamps and then the values are events, so it makes sense to order those timestamps, because it would not be a good thing if the timestamps are jumbled together, right? So it would be better if you keep it in a chronological order. Or another one would be maybe like a flight database, wherein your keys could be consist of the origin place, the destination place, and then the date and time. So you could sort the entries either through the origin, through the destination, or by their date and time. Okay, so different applications will call for the different type of ordering, so it depends. But yeah, we might want to order the entries in the map if these are the situations. Okay, so for ordered maps, it's just like a normal map, so it performs the usual map operations, but then there are additional methods. Okay, so it has an order relation for the map keys, so it keeps the map entries sorted according to this order. Okay, so that's why we also call them sorted maps. Okay, ordered maps or sorted maps. So the additional methods for ordered maps are as follows. You have the find min and find max. So from the name itself, you just return the entry with the smallest key or the minimum key, and this is possible because you have a ordering of the keys, right? If it's empty, you return null. Then for find max, it's the opposite. So you return the entry with the largest key or the maximum key. Okay, and again, if it's empty, you return null. Find less than key or find less than equal key is also two of the additional methods. So find less than key would be returning the entry with the biggest key that's less than the given key k. Okay, if no such entry exists, return null. And then for find less than equal, it's more or less the same. It's just that instead of just strictly less than, you could be less than or equal. Okay, so for example, if your keys are like 1, 2, 3, 4, 5, 6, 7, 8, and then you have the find less than 4. So 4 is here, so all of these are less than 4, right? But then the biggest key that is less than 4 would be 3. Okay, because that is the biggest among those that are less than 4, so we'll return 3 in this case. Okay, yeah, and then the opposite is find greater than and find greater than equal. So for find greater than, we'll return the entry with the smallest key that's greater than k, and then null if no such entry, and then if it's greater than find greater than equal, then it should be smallest key greater than or equal to k, and then null if no such entry. So going back to this example here, if it's find greater than 4, so all of these values here are greater than 4, like 5, 6, 7, 8 are greater than 4. But if you can what we will return is the smallest key that is greater than 4, so that would be 5 in this case, because that's the smallest out of those that are greater than 4. Okay, so yeah. And then okay, so how will we implement our ordered map? So a bad implementation would be to use unordered list or unordered array, or a hash table even, for ordered maps. And the reason for that is because they don't impose any kind of ordering for the map's keys, so they just keep it unordered, right? So from the name itself, unordered list, unordered array, and even the hash table, it was just like for separate chaining, it was a mixture, right? For mixture of keys in a certain list, or even for linear probing, it was all jumbled up, right? So it's a bad idea to use hash table for ordered maps. But what we could use would be like the sorted array, because, well, for one, it's sorted. And then later on, we'll also look at skip lists as another implementation method for, or implementation for the ordered map data structure. Okay, so yeah. So before we go to the skip list, let's take a look at the sorted array first. So for sorted array, it will have a fast search method, O of log n, because of the binary search. So you can do this because the array is sorted, and you can access the indices right away. Okay, however, there will be slow insertion and removal, which takes O of n because of the shifting of entries backwards and forwards. Okay, so although you can search for the correct position with O of log n using binary search, but then you would have to shift items either backward during insertion or forward during removal. Okay, so it's still not the best implementation, because we can do better with skip lists, as we'll see in a while. Okay, so let's take a look at the skip list. And this is not a list of things that you need to skip. So why is it called skip list. So I'll show you. So the idea is, instead of an ordered or a sorted array, we'll use a sorted or an ordered linked list. However, if we have an ordered linked list that looks like this, so this is sorted, right? 1, 2, 3, 4, 5, 6, 7, 8, and then it's a linked list. However, the problem is, if we do it like this, we are limited to linear search because we cannot perform binary search here because we can't go to the middle right away. Okay, so we are reduced to linear search, which takes O of n, and this is already worse than search table because search table took O of log n, right? But what if we could skip some nodes? So if we are allowed to skip some nodes, then we will have a faster search. So for example, if 1 had an additional node above, 3, 5, and 7 also had the same, then from 1 to 8, we could just skip from 1 to 3, 3 to 5, 5 to 7, and 7 to 8. So instead of doing 1, 2, 3, 4, 5, 6, 7 hops, you can just do 1, 2, 3, 4. 4 hops na lang. Okay? So by skipping some nodes, it allows you to have a faster search. Okay? And then if you increase the height of some nodes even more, then you can even do the skipping faster. So if you add more portals here for skipping, so you can go directly from 1 to 5, and then from 5 goes to 7, and 7 goes to 8, right? So it's even faster at this point. Okay. However, the problem is when we delete entries, if we do it like this. Okay, so for example, if we delete 5, so currently if we want to go from 1 to 6, okay, at this point from 1 to 6, we just go from 1 to 5 and then from 5 to 6. So it only takes 2 steps. But what if we delete 5? So if we delete this 5 here, this tower, so this will be removed, right? So this will be removed here. So what will happen if that's removed? So this becomes something like this. Okay. So earlier we said that from 1 to 6 we only took two steps, right? From 1 to 5 and then from 5 to 6. But if we delete tower 5, 1 to 6 will now take 4 steps. So from 1 to, well, we can't go from 1 to 3 because we can go from 1 to 3. 1 to 3, then 3 to 4, 4 to 6, right? So that's 1, 2, 3. 3 steps. So we increased the number of steps when we deleted the entry 5. Okay? So we have a problem when we delete entries because the skipping ability, or yeah, when we delete entries, then we lose towers to skip over to. So it reduces us back to the linear searching. Okay? And then when we delete more entries, then we lose more towers, and then we're back to the original one, which is linear searching. Okay, so the solution for this is to have randomized heights for each entry. Okay, so they'll have random heights so that there's no over dependence on like one tower being the big portal to go from one point and then across, so that it skips a lot of items. Okay, so just randomize the heights of each tower. So this is essentially what or how a skip list works. So a skip list is an ordered list of entries stored in a series of linked list structures. So it allows nodes to skip over other nodes during search, allowing you to run your insert, remove, and search in O of log n time. Okay, so that's faster than your search table, because in search table only search was in O of log n. Then insert and remove was in O of n. But here in skip list, all three methods potentially could run in O of log n time. Okay. So how does this work? So a skip list kind of looks like this. Okay, so we said that it's a series of lists, right? So you have the original keys of the ordered map are here at the bottom. So you have 12, 17, 20, 25, and so on. So all of the keys in the map are here at the bottom. Okay, and you'll notice that they have sentinels also, the negative infinity and the positive infinity. So those always guard the lists, the start and the end of the list, negative infinity and positive infinity. And then as you go up to each list, um, some nodes are replicated, some are not. Like for example, from list S0 to list S1, 12 and 17 are there, but 20 was not replicated anymore. Same with 39 and 50, they were not replicated. Okay, but the rest were. So 25, 31, 38, and so on. And then on to the next, it's again random whether you replicate this previous one or not. Okay, so in from S1 to S2, 12 was not replicated anymore, but 25 and 31 were. Okay, so they're still in S2 after being in S1. Okay, so this is why we have the randomized heights. Okay, and another thing you'll notice is that the last list here only contains negative infinity and positive infinity, so they don't contain any of the keys. Okay, so that's how the skip list looks like, and you'll notice each node is connected to um, previous node, the next node, and then above and below. Okay, so connected to 4 things. So formally, a skip list is a series of lists S0, S sub 1, S sub 2, and so on up to S sub h, such that each list S sub I has special keys negative infinity and positive infinity. So we saw that here, right? So our S sub h here is S sub 5. So that's our last list. Okay, and each list has the negative infinity and positive infinity. And list S sub 0, the bottommost list, contains all the keys in ascending order. So we also mentioned that earlier. All of the keys in the ordered map are in S sub 0, the first list at the bottom. Okay. So S sub 0 is at the bottom, S sub h is at the top, and we call h as the height of the skip list. So here, the height of the skip list is 5 because we're up to S sub 5. Okay. So yeah. And then each list is a subsequence of the previous list. So I'll show you that in a while. And the last list, S sub h, only contains the special keys negative infinity and positive infinity. So it doesn't contain any of the keys of the map. And skip lists are used to implement ordered maps, and they can also be used even for dictionaries. Okay, so earlier we said that each list is a subsequence of the previous list. So for example, here, this is the whole set of keys, right? And then here, it's only a subsequence of the previous list. So 12, 17, 25, 31, 38, 44, 55. So some items are already not included. And then on the next list, this is a S2 is a subsequence of S1. So from S1 we have 1, 2, 3, 4, 5, 6, 7 nodes, excluding the special sentinels. So from 7 nodes, it became just 4 na lang. So 17, 25, 31, and 55. And then from 4 here, it became 3 here, 17, 25, and 55. Then from 3, it became 1 here, until there is no more left at the topmost list. Okay, only contains the negative infinity and positive infinity. Okay, so that is the skip list. Um, so let's see the methods. How does search, how does insert, how does delete work in a skip list? So for search, let's try it with searching 50, for example. So if you want to search 50, we start at the top left. So at the negative infinity at the topmost list. And then what we'll do is we'll check forward. Um, if I move forward, will I still be safe? Like, is it still safe to move forward? That means that if I move forward, I won't overshoot my goal, which is 50. So I check the next node, it's positive infinity. So if I move forward, I will be overshooting my goal, which is 50, because this is already positive infinity, right? We'll be exceeding 50. So we won't go forward, and instead we will go down. Okay, so if we'll overshoot, go down, and then do the same process again. Check forward. Can we move across safely? 17 is still less than 50, so we can safely go forward. And then at 17, right here, so we went from here to here, right? And then we moved forward right here. We're currently at 17, so we're checking the next node, which is positive infinity, but that will overshoot 50, so we won't go forward, and instead we'll go down right here. And then at this node, check forward 25. 25 is still safe, right? We can still move forward, so we'll go here. But after 25, it will be 55 already, so it will overshoot our goal, which is 50. So we won't go forward, but it will instead go down. So down to the 25, and then check forward. 31 is safe because it's less than 50. So we'll go forward. But if we go forward further, it will already be 55. So we won't go forward, and instead we'll go down. Go here. And then check forward. 38 is safe. So we'll go here. Check forward after 38 is 44. That is also safe. So we'll go here. 44. And then after 44 is 55. So it's not safe to go forward anymore because we'll overshoot 50. So we'll go down instead. So we're right here. And then when we check the next one, it's already 50. So we've found our item, which was 50. So we found it here. So that is the process for searching. Okay. So what is the step-by-step process? So if you want to search for the key K, start at the first node in the list, S sub H, so the topmost negative infinity. And then you try to look ahead. So let's call it N, the next key, the next node's key. If the key that you're looking for is equal to the next node's key, then you return the next node's entry because you've found it. Okay? But if the key is greater than the node, the next node's key, so it's safe to move forward. So go forward. Update your node to be the next node. Okay? Because it's still safe because the key is still greater than your next node, right? So like for example, you're looking at 23 as the next and your goal is 50, so it's still safe to go forward. But if the key will already be less than the next node, then you will overshoot if you go forward, so you go down. So you go to the node below. Okay? So you either go forward or go down depending on whether it's still safe to move forward or not. So if it will not exceed the key, move forward. If it will exceed, go down. Okay, so that is the search procedure. Now how about for insert 42? So for insert, what you'll do is you'll actually need to search first for the 42, right? Because, well, it's an ordered map. You need to make sure that it doesn't exist already, right? So and the other thing is we also need to search because we need to find the correct position to insert 42 into so that we could keep the skip list sorted. Okay, so we'll follow the same procedure as search, and then so we'll start here at the negative infinity, right? Start here. If we go forward, this will overshoot. If it's here, it will overshoot 42, so we won't go forward, but instead we'll go down. So negative infinity. Now every time I go down, I will mark the node that I went down on. So I marked it here with the red triangle because I went down here. Now from this node here, negative infinity, is it safe to move forward to 17? Well, yes, because 17 is less than 42, so we can go here. Now from 17, is it safe to move forward here to positive infinity? No, because we'll overshoot 42. So instead, we'll go down to here, and notice that I've again marked it with the red triangle because we went down on this node. And then from 17, check forward. Is it safe to move forward? Yes, because 25 is less than 42. From 25, it's not safe to move forward to 55 because it will overshoot 42. So we'll go down here, and then we marked this again, okay, with the red triangle. From 25, check forward. We can move forward, but we can't to 55, so we'll go down 31, and then we mark this one. From 31, check forward. 38 is good. Check forward 44 will overshoot 42, so we'll go down, then we'll mark it. Then from 38, check forward 39 is still safe, and then from 39 we can't move forward 44, and then we'll need to go down, but since this is the last one, we'll stop here and we'll mark it also. Okay, so what did we accomplish? We found the position to insert it into because we stopped here at 39, so we'll have to insert it somewhere here. Okay, and we also marked the positions or the nodes wherein we drop down. Okay, so what will we do after that? After that, you can safely insert the node 42 here with a random height. So assuming that the height was, let's say, 4, or yeah, so we have 4 nodes here. Okay, so starting at the bottom, we add 42 after the 39 here, and then we add 42 here, add 42 here, and then add 42 here. So depending on the height, you add as many nodes according to the height, and then you connect them to the nodes that you marked. So the reason why we marked the nodes when we dropped down was because so we could connect them here. So earlier 39 was connected to 44, but when we added the 42, it's now connected to through 42. Okay, then earlier 38 was connected to 44, but when we add 42, they will now go through here. Okay, and here as well. So that is why we mark them down here, because those are the nodes that you will attach your newly added node into, so that it's not floating, it's actually attached to the skip list. Okay, so that is the insert procedure. Formally, these are the steps. So to insert entry KV, we will need to randomize the tower height. So we mentioned earlier that the heights should be random, right? So we'll repeatedly toss a coin until we get a heads. And so we'll denote with letter T the number of tails that we got, and that will become the tower height. So the tower of the entry that we're building, that would be the height, the number of tails. Okay, so T for tails and tower height. But if the tower height is greater than or equal to the current height of the skip list, then we'll have to add new lists, sh plus 1 up to st plus 1, containing only the special keys negative infinity and positive infinity. So what does that mean? So for example, your current height is s current height of the skip list is 3. So you have s0, s1, s2, and s3. Okay, so in s0 you have the negative infinity, positive infinity. This should be negative infinity also. So negative infinity here, and then positive infinities here, right? And then maybe there are towers here that are connected. Something like that. Okay, and then however, the new entry that you'll add has a randomized height of 4. So this is the new tower height. Okay, but since your new tower height 4 exceeds the current height, which is 3, so you'll have to add new lists. Oh no, I have to do it again. SO, S1, S2, S3, right? Negative inf, positive inf, and then some towers in between. Be something like that. So if your new tower height is 4, so you'll have to add new lists up to t plus 1. So you have to add so your current lists are from S0 to S3, so you need to add list S4 and S5 because it's up to ST plus 1. So t plus 1 is 5, so S5 is your new limit, like that. So when we add these new lists, they will contain only the positive infinity, negative infinity. Okay, and now if the tower height is 4, so from S0 that would always be there, for example. So and then tower height is 4, so you have 1, 2, 3, 4. So you have added the new list tower here, and the last list still contains only negative infinity and positive infinity. Okay, so yeah, and now that you have prepped the lists, um, you need to search for the key K, just like what we've been doing in the search procedure, and then mark nodes every time we drop down, just like what we did in the example. And then we'll end the search in the bottommost list at S sub 0, and then from S0 to ST, which is the height of the tower, we'll insert the node with entry KV into the list after the marked nodes. So that's why we mark them down. We mark the nodes every time we drop down because we will insert the nodes after those marked nodes. Okay, so that is the insert procedure. And then finally, for delete, it's kind of similar to search. You just have to look for the key 25. So starting at negative infinity, drop down because you can't move forward to positive infinity, and then from negative infinity here you can move forward safely to 17, but then you can't move forward to positive infinity, so you have to drop down to 17 here, and then you found 25. So from here you can actually delete this already, right? So So since you're currently here at 25, so you found it, so you'll delete this, and then you'll go down, delete this also, go down, delete this, go down, delete this. But that's not the only thing you need to do. You also need to reconnect this to this, this to this, this to this, and this to this, so that nothing gets disconnected. Okay, so this is how it will look like on the next one. Yeah, so once 25 is removed, you need to reconnect the nodes that were disconnected from your deleted nodes. Okay, so yeah, similar to search, but then you delete and reconnect the nodes. So to delete key k, search for key k and find the topmost node for k if you find it, and then delete the nodes with the key k at each level, and then reconnect the nodes before and after the deleted node. And then if there are extra lists that contain only negative infinity and positive infinity, keep only one, so remove the extra lists. So how does that happen? So for example, if we delete 17 in this case, yeah, so if we delete 17, oh, so if 17 is deleted here, 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 and here, so what will happen is for S5, it's only negative infinity and positive infinity, and for S4, since this one does not exist anymore, it's also negative infinity and positive infinity only. So we have two lists that only contain negative infinity and positive infinity. So we'll just delete this extra one, and we'll keep only one extra layer that has only negative infinity and positive infinity. Okay, so that's what we mean by that. So yeah, that is the process for deleting keys in the skip lists. Okay, now for the implementation, we will use something called the quad node, and it's called the quad node because it's connected to 4 things. Okay, up, down, left, and right. Then you also contain the entry. So the 5 properties of the quad node are the entry, a link to the previous and the next nodes, that's the horizontal direction, and it also has links to the nodes below and above, which is the vertical direction. Okay, so for the methods, you can call next node, previous node, those are found on the same level, and then for below node and above node, those can be found on the same tower. And then if you want to get the entry, then just call entry of the node. Okay, so those are the methods for the quad node. Now for the performance of the skip list, we used randomization for the heights, right? So the actual running time depends on the actual random numbers of the heights of the outcome of the coin tosses. So if we think about it in the worst case, the running time would be O of n, which is linear time, and this happens when all entries have the same height. But this is a very low probability of happening. So what do you mean by this? So for example, at when we inserted the first entry, it has height of 3, and then the second entry also has height of 3, third entry also has height of 3. Now if this is the state of our not hash table, the skip list, then we are reduced basically to like a linear search, right? Because the difference in heights is what allowed us to skip. But if they have the same height, then we'll be seeing all of the keys at the same level, right? So if we have varying heights, this allows us to skip some nodes. Like for example, you can go from here to here without passing through this one, right? Or from here to here without passing through this one. But if everything is the same height, then you'll have to pass by everything, right? But the good news is that having all entries have the same height only happens like if you have really bad luck. So that has a very low probability, uh, low chance of happening. Okay, so we don't really need to worry much about the worst case running time. In practice, the search, insert, and delete methods will run in O of log n time with randomized heights. Okay, and for the extra memory, it will take O of n because of the extra towers that we are using. And although not all of them will have like what do you call this, tall heights, so some of them will be short, some of them will be tall. um, in total, that would be an extra memory of O of n. Okay, so that is for the performance of the skip list. And that's it for this video. So to review, we talked about a lot of things in this video. So first, we looked at hash function and how it transforms a key of any type to an integer in a range O to n minus 1. And then we used the hash functions in hash tables. So hash tables are basically hash function plus an array called the bucket array. And then we looked at two different ways to handle collisions in hash tables. First one was separate chaining, so you keep a different list at each bucket. And then for linear probing, you only have one entry per cell, but then if that cell is occupied, then you look for the next available cell, right? And then you also looked at ordered maps, wherein it's just like a map, but then the keys are ordered or sorted in some manner. And then we looked at skip lists to implement the ordered map. And the basic idea is you build a randomized height for each node so that we could skip over some nodes during search. Okay, so that's it for this video. For our next topics, we'll talk about trees. So talk about binary trees and some tree traversals. So yeah, that would be for our next video. So yeah, that's it for this video. If you have any questions, please don't hesitate to ask me, and I will see you in the next one.